Hi there. This is going to be a discussion of, we did the common emitter in class with a passive load. Passive load means that the thing above the transistor, if you're using an NPN, the thing above the transistor is a passive device, which a resistor is. We may have some interruptions from dogs and birds, but we'll get through that. Okay, so first, I think it's worthwhile going back and just doing a quick review of the, if this works, of the passively loaded. Oh my goodness. Okay, so this is a large signal. We'll call it large signal. Yeah, hi there, Fifi. Yeah, not right now. Go attack your brother. Go attack your brother. Okay. So this is this model right here is good for working with currents and voltages. This works great, but what we're doing for the analysis for most of the rest of this class is the small signal analysis, and that means we only care about the moving parts. So again, small signal, we only operate in a linear region, and that means that we can use superposition to take the circuit, divide the circuit into two pieces. It's actually the same circuit, but two different representations of the circuit. One for DC values, which this one can help you with, and then one for AC values. For AC values, this representation of a transistor doesn't help you all that much. So you need to go with a model that's made for small signal analysis, and probably already seen that, but haven't really had it explained what it means. So we're going with, that's our circuit. Okay, the view of a transistor that we want to use for small signal analysis looks like this. If I can draw it, we have a current source here. That's a current source. GMVBE. And here is VBE. I'm assuming that most of you have already seen some of this, so I'm not explaining this, in detail. But there's the base. Down here is the emitter. And then you also have this guy over here, RO. And a lot of people make the mistake of calling this RO the output resistance of a transistor. Yes and no. What this is representing right here, that is actually representing the effects of base width modulation. And when we go into detail of the model, you'll see why that's so. But this represents base width modulation. This represents the change in current due to changing VBE. Now, if you remember, it's VCE that affects base width modulation, or causes or makes the change in current due to base width modulation. So this branch right here represents the current contribution to IC from base width modulation. This branch right here represents the current contribution to IC from the change in VBE. So here's our transistor model for small signal. Okay, so let's put that in there. So that's our representation of the transistor that's useful for small signal analysis. We can make this a little smaller. So those are the two important drawings so far. Okay, now you have those two drawings. We are now going to analyze the small signal picture of this circuit right here. Now to do that, remember superposition, we zero all the sources except for one and do analysis. if we're doing the small signal analysis, we only care about the moving signal. So here's a moving signal that's a source. This is the result of moving this one. So this isn't a source. This is your source. So you zero all the sources except for this one. You say, well, there are no sources. Actually, there is. This right here, this V supply, that is a source. It's tied to some supply someplace. So this right here, if you zero a voltage source, then you're grounding it. So what this turns into, let's go back over here. That's not bright enough red. There's bright enough red. When you're analyzing this circuit as a small signal model, anything but VN, so VN stays in your picture. Anything else that's a voltage supply, that is considered ground. And this is called an AC ground. In other words, kind of a high frequency ground. Or the other name that you hear it called is a virtual ground. Virtual ground. This is when you really appreciate tablets. Okay, so let's do a little bit right there. And move that down. Okay, so that's the new picture right there. And it's kind of misleading for me having drawn this on this picture right here, because this is not where you do small signal analysis. This is, again, where you figure out the biased voltages and all that. To do the small signal analysis, what you do is you take this picture right here, and replace the transistor with your small signal model right here. So let's do that. So I am going to take V out, we'll move it over here. Take V in, move it over here. Ground, we'll move it over here. Now in place of all of that, this just goes right up here. Okay. And remember, the resistor was connected to the collector, so you connect the resistor to the collector. The emitter was tied to ground. I guess I should try this in a different color maybe. So this goes here. This is connected to ground. V in went to the base, so that's good. And then V out was connected to the collector. And that's your new picture right there. Okay, I'm not sure how long YouTube lets you post, how long the videos are that YouTube lets you post, so what the heck, we'll keep going and I'll just split it, otherwise let's see. Let's see, so now we've got our picture like that. One thing we see here is that here's a node, this is V out. If you look at, let's see what's connected to V out. V out has a resistor connected from V out to ground, going through RO. So here's the node V out. Here's a resistor connected to ground. If you look over here, here's V out, here's a resistor, and it's also connected to ground. So actually this resistor right here and this resistor right here end up in parallel. So we can get rid of, I'll go over here. We can pick a new color. Okay, we can get rid of this, and we can put that in parallel over here. And now let's cut this so it's not confusing. So we basically moved this resistor in parallel over here. So let's take that. Okay. All right, now we've kind of got this as pretty as it can be. And now we need to do KVL, KCL to figure out some important values. And since the next few topics we're going to do are loading, loading, and loading, to understand loading, you need to know RN and R out. And RN, just use this. So RN, and I'm going to use a capital RN because this is a representation of not just a single transistor, it's a representation of an entire circuit. So I'm going to use a capital letter to represent that. If I had a small r right there, it would mean that it's representing the RN of a single transistor. Okay, so RN, we're going to use two-port rules. So we have is change in V in, or not a V oin, not an I, over the change in I in. Okay. Okay, next thing you have to figure out is what exactly is Vn. Here's Vn. That's pretty straightforward. And now you have to figure out what IN. Now we need to label it. So let me go back over here. When you say IN, you always want to label it into the circuit. So this would be IN. You're giving it Vn, but because you're giving it Vn, there's some current that goes in. We'll call that IN. You're not supplying IN, but it's there because of the voltage that you're supplying. Also, just as an aside, when you define I out, it goes this way. It goes out of your circuit. Okay. Okay. All right, so your Vn, your IN, and these capital letters right here, that's like a complete circuit. But when you're drawing this small signal model, I should have drawn these a little bit different. Let me make these prettier here. What I should have drawn is, just to make it clear that this was a lowercase, I should have like this. And when I write this out in a lowercase, that means it's just the moving part of the signal. So lowercase here, we've got a whole bunch of things going on. Lowercase currents and voltages here, that means that it is just the moving part of the signal. We've gotten rid of the DC part. This is the small signal, essentially. Big, say R in, big R out, capital R out, capital R in. That means it's an R in or R out for a complete circuit, not just a single transistor. A small GM or a small RO, that is just for a single transistor. So remember that transistor that we had? Remember this transistor we had right here? If I'm describing the characteristics of this single transistor, those characteristics are written in lowercase. Okay, so we're down to here. We've got our Vn, In. Let's make this a little smaller so I can do my equations on the same page. Okay. So now when I do this, what I want is an equation. Let's do this right out. Because the lowercase letters are already the moving signal, the change in the signal, this is what we want. Rn is going to be the small signal. Should I put small signal over here? Small signal. Small signal. Okay. So we need an equation, Vn over In. Okay, so that's not, it is pretty straightforward if you know what you're looking for, but let's do the math here. This is I don't like this bug, where the pointer stops working when you're using pictures. Okay, so let's see. It's not really directly, clearly relatable, but we know we want an equation with Vn and In in it. So we look over here. Let's see here. Oh, I forgot to label this. Alright, one more thing. Let's do... No, it's not going to let me adjust the size. Good. Okay. Yeah, whatever. Oh, there we go. Okay, and this is our pi right here. It's not very big. Okay, so what you can do here is even though you don't have, like, it's not exactly clear what Vn over In is, you can relate these two with an equation here. So I claim that Vn equals In times R. Oops, where's pi? Here's pi. R pi. Okay, that's it. There's Vn on this side of the resistor and ground on this side of the resistor. So just using Ohm's law, I can come up with this. Now, if I rearrange that, so what I'm looking for is an equation that says Vn over In. So if I divide both sides by if I divide both sides by In, then I get equals R pi. And hey, that's what I was looking for. I was looking for Vn over In. And now you can see that Vn over In is R pi. So Rn small signal equals R pi. Okay. Can we make this even smaller? Get all that work on one page. Okay. Alright, so that's Rn. So there's a couple other values you want. R out is 1. R out has this handy little thing that you get to use called two-port model rules. So your R out equals, and you get to V out over I out. But remember, these right here are, let's use the other picture. How did I make it pretty? I didn't. Okay, let's do over here. Okay. All right. And notice these are small signal values. Guys. Quiet, guys. Okay. So you want V out over I out, but since those are already the moving values, to get is I out. Okay. Now it's not instantaneously clear how to get what V out over I out equals. So first thing you want to do is just find an equation that relates V out and I out. But one thing that I forgot to put here is that we are going to use two-port models. So what that says is that to find R out, you set V in equal to 0 and then try to find V out over I out. Okay, so let's see. If we set V in equal to 0, I think I'm out of colors here, so I'll use this one again. V in equal to 0, that means you're grounding it. Okay. Okay, now since you grounded it, let's see, what's VBE? The base voltage is 0, the emitter voltage is 0, so the voltage across here is 0. So VBE equals 0. So we get to, is there an X here someplace? Not really. I guess we just draw it. Okay. Make this big and red. Okay. And then, so since VBE equals 0, there's no current going across there. So it's like, this really doesn't have all that meaning. But if VBE is 0, then 0 times GM means this goes away. And this is gone too. Okay, so let's see what's left here. If you get rid of those two things, all that is left. Buddy, no! Buddy, no! Buddy, no! Okay, so once you zero those two things, what you get is this. Okay. Okay. Now let's find that equation. Alright, so we need something that relates V out and I out, and hey, it becomes pretty friendly here. If I can type right. Okay, so to find an equation that relates V out and I out, I out times RO Okay, that's not quite what we want. We want V out over I out. So if you divide both sides by I out, we divide both sides by I out. Divide both sides by I out, then you get this, and then we know that R out equals V out over I out, and here we have V out over I out equals this, so that's your equation for V out over I out. Alright, in class we did GM, so I won't do that here. Let's do one more example here. This is, if you remember what we started off with, a common emitter with a passive load. In other words, the thing that comes above the transistor, that's a passive element. It's a resistor. Okay, let's try using an active load. And there's a number of reasons why you use an active load. They are listed in the handout, so I'll let you look at them there. Now let's try let's first draw it. Okay, so if you're going to draw it, you get rid of the resistor and you draw in a transistor. Okay, the trick is that you want to we haven't discussed why, but you want to use a PNP for this load. We'll talk about that at some point. And then you're going to need to bias the PNP. And one of the easiest ways to do that is you want the PNP to be in forward active. And maybe a resistor here to drop the rest of the voltage. Here's an NPN. So you're biasing for your NPN down here. This is the complete circuit will probably look something like, we're ignoring the biasing circuitry. Actually, you probably want a resistor here and all sorts of other things. I'm ignoring a bunch of things right here. We probably want RB. We probably want resistor here and a resistor here, so the signal goes directly over to your amplifier. Okay, so now we have VN going on to here. You have the same current through both of these. So you have this calculating the VBE for your PNP, and then you have this calculating your VBE for your NPN. Ask me about this if it doesn't make sense. Okay, so that's what we're actually doing. I hope you can hear over the birds. We are kind of ignoring all of this. Gabby! 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 Okay, this is the circuit that we're looking at. We're assuming this is that VB is a DC voltage. Okay, so let's take that. That's our new starting point. I know I'm going a little bit quick, but okay. So just finished finding the R in and R out of a passively loaded device. Okay, here's our new device. Now we have to draw the small signal model. Let's see, do I have one up here? Yeah, so let's go back. If you remember, this was your NPN. The only thing that's different now is you don't have an R here. There wasn't an R up top. What you have is a PNP. So just like when you're using actual transistors, you flip everything over. So one way you can get the model here is all the letters are going to be flipped too, so we'll have to fix that. But okay, so this is your NPN. To get the PNP, I'm pretty sure it's not going to fit either. Let's move this down just a little bit. Let's do. Okay, so there's your NPN. What you do is you flip. There's your PNP. I'll get rid of that. everything's flipped. So this used to be plus, now this is plus. That used to be minus, so that's minus. Here's your base. Okay. And, oops. Okay, and then that's the color. Okay, so there's your PNP. You just turned it upside down. And what's up here is VCC. Okay, if you look at this diagram right here, the collector of the PNP is connected to the collector of the NPN. So let's see what that is. So here's the collector of the PNP. Here's the collector of the NPN. So, alright, and let's see, nothing's changed to the NPN. You still have V in coming, I should be looking over here, sorry. You still have V in coming into the base of the NPN, still have the emitter of the NPN connected to ground, still have the collector of the NPN going to V out. Let's look at the PNP now. Okay, the collector of the PNP is connected to V out, so that looks good. The emitter is connected to VCC, so that looks good. And then the base is connected to this bias voltage. Now if you remember, the bias voltage was a DC voltage, and when we're doing small signal analysis, what do we do to DC voltages? And I hear you all saying, you ground them. They are AC grounds or virtual grounds. The only supply we keep is the moving supply, which is V. Any DC source. Okay, go attack your brother. Go attack your brother. Yeah. Hi guys. Hi guys. Okay. All right. So this is our new picture here. Oakley. Oakley. Go attack your brother. Where'd you go? Where'd you go? Oh, I don't know where it went. Okay, so this is our new picture. Oh, goodness gracious. There's our new picture. Alright. And this is just the small signal version of this. Oh, I forgot. I'm probably saying you forgot to ground VCC. Yep, any DC source becomes grounded. So let's do that. Okay. Yeah, any DC source is grounded. So there's our original circuit. Replace things with small signal model. Okay, so let's see. Can we get rid of some stuff? Let's go borrow this. So if you're looking at this, alright, so let's see. Is there anything we can get rid of? Let's see. Up here, let's see. The emitter of the PNP is ground, AC ground, virtual ground. The base is ground, so oops, this goes away. Okay, if B and E are both ground, VBE is 0, so that goes away. Now let's see what we have left. See what we have left. The GM source right here and R pi go away. So let's see what happens when we get rid of those. Let's get rid of all of this. And R pi, or not, I mean, is over here. that goes away. And you should be, right about now, you're thinking, this looks pretty much exactly like the passively loaded common emitter amplifier, except instead of R, there's RO. Okay. So this is exactly the same as the common emitter amplifier you just did analysis for, except instead of R you have RO. So let's move this down a little bit. Okay, so that's after simplification. Okay, so after simplification, it looks just like what you had for your passively loaded common emitter, except for RO. So let's see what happens now. If you take this and you say, well, it's also going, just like with the common emitter with the passive load, this resistor is going from this node to ground, just as RO is over here. So you can put that in parallel. Now the difference is, if you remember, when your R, if you put up here, if you have a big R right here, it can force your transistor into linear, or you can raise this. You can raise the supply voltage to keep that from happening. So if you have a resistor very big at all, like I said, either you have to raise the supply voltage or you face the danger of putting your transistor into linear. Okay, with an active load, a couple of good things happen. One is that across here, for this to be in forward active, which is where we want it to be, if it's in forward active, all you need is VC sat across here, no matter how, well, you shouldn't say how big the resistance is. Yeah, so how much, no matter how big the perceived resistance is looking into the collector, all you need is a VC sat across that. But with the actual resistor, you need V equals IR volts across it. So that's the first thing. You don't need as big a drop of voltage across here. Other thing is that, again, you can't make R very big, but your R naught, you didn't do the equations on here, but your R naught, that can be, since we're using 50 milliamps, it seems pretty small. It's just a K or 2 or 5 or 10. But if you're using a smaller current, it turns out that it can be a mega ohm or hundreds of mega ohms. So what you've just done here is you've increased this R out by quite a bit. And now you say, well, what's the good of that? Let's see, so a little bit more math here. The good of that is, so we have one thing that we haven't calculated, that's gain. And that one is your V out, if we're working with voltage amplifiers, V in. Okay, so that's the definition that you know of, but let's break that into two parts. Let's break that into delta, let's do I out over V in, and then let's multiply that by V out over I out. Okay, so if you look at this, you can see that the I outs cancel out, and you get V out over V in. So this is saying the same thing as this, except I've just made it longer. Okay, if you do that, if you look at this, change in I out over the change in V in, that is just VM. Okay, and the change in V out over the change in I out, that's just R out. Okay, so in class we calculated GM, and assuming Dr. Pradnov's class has already looked at GM, but right here what this says is the gain is GM times your R out. If you make R out bigger, that gives you more gain in general. And there is a trade-off. I out actually cancels out in these things, but R out is one of the things that can give you a bigger gain. And what you did by using an active load now is, before it was your R in parallel with R out. If R out, doesn't matter if R out is a mega ohm, if it's in parallel with 1K, it's going to act like a 1K resistor. The 1 mega ohm isn't going to have much effect. But if you have 1 mega ohm in parallel with 1 mega ohm, now you have 500 k ohms right here. And when you put it into this equation, it gives you a big gain. So, moral of the story is active loads, exact same analysis as a passive load, except you use RO instead of R. It gives you a giant resistance, which makes your gain big. But it gives you that big resistance without a big drop across it, so you can still keep a low supply voltage and a low power. Okay, I'm going to do one more video on the follower. Okay, so give me a half hour or an hour on that one, and it'll be up soon. All right, thank you very much.